Next, we will consider a case where there is a distribution about the local frame, a molecular orientation distribution about the local uniaxial symmetry axis. So, for example, if consider the case of a collagen fiber comprised of many individual fibrils of triple helices, and the objective is to make measurements of the local fiber polarization dependence and then relate those back in terms of the distribution of individual collagen fibrils within the fiber. So this is just a nice illustrative example. So how do we approach this? Well, it's a little bit different than in the P212121 crystal case, because now we have a distribution of orientations as opposed to of molecular orientations as opposed to delta functions which are present in a lattice. So how do we handle that distribution? Well, it manifests as an orientational average. And there's three Euler angles we're averaging over, theta, psi, and phi. It turns out that we can separate them out really cleanly using tricks in linear algebra. And as long as these two orientations are distributions are separable, in other words, the orientation of theta and psi is independent of the distribution of orientations in phi, then we can evaluate these two expectation values independently as well. So we can write the total orientational average as an average over theta and psi, and then a separate average over phi, where phi is the azimuthal rotation about the one unique symmetry axis of the collagen fiber. And we can now, as long as we know that it's a uniform distribution consistent with uniaxial symmetry, then we can evaluate that triple Kronecker product averaged over a uniform distribution explicitly. And when we do, it turns out that we have a grand total. If we look at this, do this orientational averaging, it turns out that a grand total of only 7 tensor elements survive inside the local frame from this averaging over all of these distributions in phi. All the rest of the 26 just disappear by nature of that averaging. We can generate that full set of 27 from the smaller subset of unique non-zero elements. And now in the most general case, that'll be 7. If we're talking specifically about second harmonic generation, that only 4 non-zero tensor elements that are unique contribute to the local frame response. But we can populate the full set of 27 through this sparse matrix Q. And this is very analogous to what we talked about previously with the symmetry matrices. So what does that Q look like in the presence of this orientational averaging? Well, if you explicitly evaluate this triple Kronecker product averaged over phi, then this monstrous table of zeros and small things and one halves and one shows up. I'm just including this simply to illustrate that that when you evaluate this triple integral, the 7 unique elements that survive are the ones that don't have all zeros across every row. So, for example, XXZ has 2 contributions, each of which show up at 1/2. ZZZ has a 1, and all these other terms have factors of 1/2 throughout them. Now, there's still the remaining orientational averages over theta and psi. We've only done the averaging over phi. And if we include explicitly the contributions of all 27 elements to the remaining, if we explicitly evaluate the remaining orientational averages for theta and psi, then this is what we get for the four achiral present, the 4 tensor elements that are present in achiral uniaxial local assemblies. Now, collagen's chiral, so it might have the potential for additional contributions, but this is the most general case of some frequency generation, all of the tensor elements that could be contributing in the molecular frame and relating those back to the local frame response. In chiral films and in chiral assemblies, including collagen, there is an additional possibility for some contributions arising from the nature of chirality within the molecular frame and ensemble frame. All right, let's go back and work an example. And we'll start by making a couple of assumptions. First of all, let's assume that we make a measurement and that the intensity of the SHG polarized co-parallel with the fibril axis is 10 times as large as the intensity polarized along the fibril axis when orthogonally polarized light is coming in. In other words, we're detecting co-parallel with the fiber axis but illuminating cross-polarized to it with the fundamental, and we're doing second harmonic generation, so a common measurement. We make this measurement, it's 10 to 1. What is the mean fibril orientation angle if we assume a narrow distribution of fibrils, and if we assume that at the individual fibril level, beta ZZZ is the one dominant tensor element describing the fibril nonlinear optical response. So that's the framework. How do we proceed forward? Well, first of all, we can look at these and bear in mind that what we're talking about when we look at these intensities, these will be proportional to chi z z z over chi z x x equaling 10. I'm sorry, squared equaling 10, because the intensity is proportional to the tensor element squared. Or in other words, chi z z z over chi z x x square root 10. There's sign ambiguity. It could be plus or minus square root 10, but we'll just leave it at that for now and move forward. All right, so if that's the ratio, then how do I use these orientations to say something about the orientation relative to the fibril axis? Well, we can go back and look at these orientational averages and what connects the molecular frame to the local frame in each of these cases. And it turns out from those orientational averages that we get the following. Chi ZZZ is equal to cosine cubed theta, and chi ZXX is equal to 1/2 sine squared theta cosine theta. If we have a narrow distribution in orientations, then this ratio, which is roughly equal to the square root of 10, that's going to equal roughly 2 cosine cubed average value of theta for a narrow distribution of theta. So we can just move that expectation value over, and then sine squared theta cos theta. Or in other words, 2 over tangent squared theta. Now when we evaluate, we have square root of 10 equaling all of this. There's really only one unknown in this equation, and that is the expectation value of theta. If we go ahead and solve for it, we get this. Expectation value for theta is roughly a tan of the square root of 2 over root 10. And that, if we just plug and chug, turns out to be roughly 38 degrees. Let's take the same results and make a different assumption and see what that gets us. Let's assume instead we still have the same measurement of the ratio, but instead of asking what is the mean fibril orientation angle in the limit of a narrow distribution of fibrils, let's consider again the alternative question. Let's assume that we know that the mean orientation of the fibril axis is 0. In other words, on average, they are coparallel with the fiber axis. But the one reason that we're not getting the exact beta ZZZ result is because there's some spread about that mean. In that case, our distribution in theta is not going to be a delta function distribution as we assumed previously, but it will be some, for example, Gaussian distribution centered about 0 with a distribution with the 2 sigma squared. And n is just a normalization constant. So if we look at the same results and interpret them this way, then now this 2 cosine cubed theta over sine squared theta cos theta. If we explicitly evaluate, it's going to look like this. The integral is from 0 to pi, and then cosine cubed theta is the expectation value we're trying to pull out. We multiply this by sine theta, e to the minus theta squared over 2 sigma squared d theta. And that factor of sine theta comes from the fact that we're integrating over spherical coordinates. And so that's part of the Jacobian of the integration. All right. Oh, don't do that to me yet. All right. Now, there's no easy thing to do except for numerically integrate this thing rather than trying to, that's the grand total of the simplification we can do. We can numerically evaluate this integral as a function of sigma to define the place where the ratio of these two elements is equal to the square root of 10. And if we do that, we get the following. It turns out that you have to go to a very broad distribution of orientations to start approaching this value of the square root of 10, suggesting that there is, in this measurement of a 10-to-1 ratio, a very broad distribution of orientations would be consistent with that observation, or a very narrow distribution centered around a mean tilt angle of 38 degrees. But this gives some insight into how the polarization dependence can be related back to the molecular orientation distribution In a practical case, such as the orientation distribution of fibrils in collagen relative to the fiber axis.